Welcome! This is the video tutorial series on the rolock bond construction technology, presented by Scott Rwanda and the ProEco program. Part 1. Rolock bond design principles. In this video, we will break down the rolock bond technology in its building components and analyze its constructive principles. We will start with the rolock bond brick. We will continue with the rolock bond wall, and we will analyze its anti-seismic properties. But before we start, it's worth spending a few words on the historical background of this walling system. Going back to the early 1800s, we already have examples of this technology being adopted for its cost-effectiveness in the construction of townhouses in central England. A few years later, in Ontario, Canada, we have another example of building using the rolock bond technology, most likely benefiting from its insulating properties through the use of its masonry cavities. Another remarkable example is this apartment complex built in Chicago in 1949. The typical masonry cavities have been filled with cement to improve the wall compressive strength. The rolock bond technology offers excellent resistance against seismic events. For this reason, it was the technology of choice for this apartment building in an earthquake-prone city like Kathmandu, Nepal. The first Rwandan building featuring the rolock bond technology was built in Rusizi, in the southwest of Rwanda. There is an abundant series of examples of contemporary architecture adopting this constructive system, at all latitudes and in a wide variety of shapes and forms. The overall benefits of the rolock bond technology are not limited to the reduction in materials used, notably the cement required for the wall construction and for plastering, but its benefits extend to a significant reduction in embodied energy and green gas emissions. Let's now focus our attention on the rolock bond brick. This technology relies on this specific brick type, with key features like a consistent size of 21 × 10 × 5.5 cm and a consistent compressive strength of about 10 MPa, often more than double compared to the usual 3 to 5 MPa of a traditional brick. The reliable performance is guaranteed by a standardized industrial or semi-industrial production process. This ensures the structural stability of our load-bearing brick wall. As mentioned earlier, the brick manufacturing happens in a controlled environment, where the raw materials are mechanically extruded, properly dried and fired. The firing happens in a kiln where temperature and time are constantly monitored. The perforations within the brick body allow the heat to reach the brick core, ensuring an evenly fired product. Both during the quality control process as well as when they are delivered on site, the bricks undergo a selection process where the sizes are controlled against the given tolerances, and underfired, overfired, as well as damaged bricks are discarded and set aside for different uses. We are now on site and we are about to start building our rolock bond masonry wall. This bond appears similar to a Flemish bond, stretcher, header, stretcher, but with a shiner, rolock, shiner orientation. Basically, the bricks are laid on their shorter side rather than laying flat as in a typical bond. This specific way of laying out the bricks allowed to build a 21 cm wide wall, leaving a cavity in between the shiners. Let's see it better in this animation. The modular arrangement of 2 shiners and 1 rolock is repeated linearly along each brick course. The next course will then be shifted of half a module, in order to achieve the typical alternating pattern. This leaves us with a continuous internal cavity of 10 × 8.75 cm running throughout the wall height. Alternatively, the repetitive pattern can be replicated by using larger fire clay blocks called plan fills. These blocks are the equivalent of 3 bricks, as the mortar joint is replaced by a solid fire clay joint. They can significantly increase the masonry compressive strength, as well as reducing the construction time. Keep in mind, however, that these blocks are more difficult to source and to produce by small and medium-sized producers, limiting their overall diffusion in the market. We can then see how the rolock bond measurer offers the same load-bearing features of a standard brick wall, while using 30% less material thanks to the cavities and the reduced number of mortar joints. The voids left during the measurer construction run vertically along the wall, but not only that. Diagonal cavities as well as alternating cavities, for electrical wires for example, can be used. Continuous horizontal connections instead can be achieved by modifying the measurer and substituting the rolocks with portions of bricks. So you might wonder, how many bricks do I need to build a square meter of wall? The number is 100 bricks. So make sure you order all the bricks you need in advance from your local producer. To simplify the procurement process, we can do a simple calculation where perimeter and height of the building can be multiplied to quickly obtain the total measuring surface. We then factor in an extra 10% that takes into consideration discarded and broken bricks. Lastly, we multiply the total by 100, the number of bricks per square meter we established in the previous slide. This gives us a quick but useful estimation of the bricks required to complete the construction, and we will be sure to place an order of the correct quantity. A similar process can be followed for a larger building. In this example, a G+3 apartment block requires about 100,000 bricks. We mentioned earlier the anti-seismic properties of the rolock bond technology. This is true despite the apparent absence of typical structural reinforcements we might expect to see in a brick building. The reinforced concrete frame is concealed within the walls, exploiting the cavities typical of this masonry. The result is a compound structure that can withstand both the vertical loads through the load-bearing masonry and the shear forces of a seismic event through the reinforced concrete three-dimensional frame. The vertical components of the reinforcements are typically located in the corners and in the wall connections. Their specific position is derived by the position of the cavities. Horizontal connections are located, on average, every 12 courses and in correspondence of doors and window sills and lintels. This is also where vertical and horizontal reinforcements connect. The result is a three-dimensional reinforced concrete truss, embedded and perfectly bonded to the masonry. The vertical reinforcements stem directly from the ground beam and move upwards within the masonry to connect with the horizontal elements. In this configuration and using the bricks described in this video, the maximum suggested number of stories is 3. The main limiting factor are the brick compressive strength and the building footprint. Using a brick with a higher compressive strength, like the Planfield block for example, can lead to a height increase up to 5 stories. We remind you though that this must be always verified with a structural engineer. This topic and many other will be covered extensively in the upcoming episodes of this video tutorial series. Thank you.